Hi everyone, this is video number 11 of our P3 complex numbers lecture. On the screen right now is page number 30 of P3 tutorial 10 notes. The contents of page 30 is to prepare ourselves with some knowledge on geometry so that we can tackle the more challenging questions involving locus on Argand diagram. Okay, so the title of page 30 is Maxima and Minima. Maxima is just the plural form of maximum. Minima is just the plural form of minimum. And so here we are concerned about finding maximum and minimum distance, maximum and minimum angle and all that. Right. So let's see what to discuss here. In part A, we first consider this situation. If given a circle with center C and a fixed radius R, how do we measure its shortest and longest distance from a fixed point P which is outside the circle? Okay, so it means if we are given a circle with center C and a fixed radius R, then how do we measure its shortest and longest distance from a fixed point P which is outside the circle? And so they say there is a point P which is outside the circle. That point P can be anywhere outside the circle. I'll just put it randomly here. Okay. So first of all, we have to understand what is meant by the word circle. The word circle always refers to the circumference of the circle. Okay, so what is the shortest and longest distance from P to the circle? Okay, the way to measure this distance is to construct a straight line that connects P to C, and you extend the straight line to the other side of the circle. Okay, I will call the intersection point here to be A. I will call this intersection point to be B. Okay, now PA is going to be the shortest distance. Okay, so shortest distance from P to circle is going to be PA, and the longest distance from P to circle is going to be PB. So this is the way to find the shortest and longest distance from an external point to a circle. Now, why is it that A must be why must we take PA as the shortest distance? Why can't we take P to, let's say, A prime here? Okay, the way to explain this is not too hard to understand. Okay, so we know that if we draw a tangent line, tangent to the circle at point A, and because CA is the radius, there will be a 90 degrees here. There will be a 90 degrees here. And of course, 90 degrees on the other side as well. Okay, so now if I connect a straight line from P to A prime, then if I enlarge my diagram big enough, you'll be able to see that we actually have this intersection point between my light blue line and the orange line. Let's call it D. Okay, PD is the hypotenuse of a right angle triangle. PAD is a right angle triangle, and because PD is a hypotenuse, PD must be longer than PA. PD must be longer than PA. Because PDA is a right angle triangle, and the hypotenuse side is always a longer side in the right angle triangle. Okay, then, because PA prime is slightly longer than PD, so we have this inequality relationship. PA prime longer than PD, PD longer than PA, which means PA prime must be longer than PA. And so this explains why we must take the distance PA as the shortest distance from the point P to the circle. If you take any other point on the circumference of the circle which is not A and connect it to P, that distance must always be longer than AP. So AP is the shortest possible distance from P to a point on the circumference of the circle. Then the furthest point, the furthest point from P to the circle, it will be on the opposite side. It will be on the opposite side of the circle, which means AB forms a diameter. And so PB gives you the longest distance. Now, how do we find the distance PA and PB then? I'm trying to scroll to the left. Yeah. And so how do we find PA and PB then? We'll have to make use of radius. Okay. So we have a radius here from C to A, and we have another radius here from C to B. So usually, the center of the circle would be known. Point C would be a known coordinate. Point P is usually a given point with known coordinates. So PC, the distance PC, it will be easy to find just by using the coordinates of P and C. Right? So to find PA, you just need to take PC minus radius. Just take PC minus the radius. And PB, you will just need PC plus radius. Because PB is just PC plus CB. And we know CB is the radius. Yep. And similarly, PA just now is PC minus AC. And we know AC is the radius, therefore it becomes PC minus R. So that also means shortest distance from P to circle, it is PA, which is also PC minus R. So this is in fact PC minus R, and longest distance, this is in fact PC plus R. So these are the things that you need to know for distance from external point to circle. The shortest distance is PC minus R, longest distance is PC plus R. Okay, now let's move to part B. Given a circle with center C and a fixed radius R, how do we measure its shortest distance from a fixed line L, which does not intersect or touch the circle? And so here again we have a circle. And this time we have an external line. That doesn't intersect or touch the circle. Okay. You have line L. This is circle with center C. Okay. So the shortest distance from the line to the circle, shortest distance from line L to circle. The way to get that shorter distance is this. You would construct a perpendicular line to L from the center C of the circle. You will construct a perpendicular line like this. Then let's call this intersection point as A. And let's call this foot of perpendicular as f. Right, so the shortest distance from line L to the circle will be the distance FA. Right, so yeah, this is all that you need to know for this part. It's a distance FA. And how to get this distance FA? You first start by constructing a perpendicular line from the center C towards the straight line L. And then the distance AF will be the shortest distance from the line to the circle. Okay, under what type of question would you need this knowledge? Okay, for example, in certain past year question, they might ask you to draw the locus of Z. And so this circle can be the locus of Z. And they would ask you to draw locus of another complex number, for example, locus of W, which happen to be some perpendicular bisector. So your locus of W could be this one. Okay, so let's say in the past year question, you have already drawn the Argand diagram, and you have locus of Z being a circle, locus of W being a perpendicular bisector, which is also a straight line. Okay. Then they might ask you to find the minimum value of modulus Z minus W. So you will need to know how to interpret this modulus expression. Okay, so recall that when you have modulus of something minus something, this actually means distance from W to Z. It's a distance measured from W to Z. Now, if your straight line L is the locus of W, then there are infinitely many possible positions of the point representation of W. Okay, so your W can be here, W can be here, W can be here, W can be here. Okay, there are so many possible positions of W. And then similarly, there are many possible positions of your complex number Z. Z can be anywhere along the circumference. You can have Z here, Z here, Z here, and so on. Okay. So there are actually infinitely many possible values for the distance from W to Z. You could have taken this distance as a distance from W to Z. You can also take this distance as a distance from W to Z. So there are so many possibilities. And so from the infinitely many possibilities of distances from W to Z, among so many possibilities, which would give you the shortest distance? It is actually the AF. It's actually the AF. Because A is a possible position for Z and F is a possible position for W. Okay, so the distance AF would give you the shortest possible distance measured from W to Z. Okay, because W can be anywhere along the red line, Z can be anywhere along the circumference of the circle. Okay, so the shortest possible distance from W to Z, it will be the distance AF. Yeah, so in this case, the minimum value of modulus Z minus W, it will be the distance AF. And then you will make use of your Argand diagram to calculate the distance AF. Yeah, and you will need to calculate it out. You are not allowed to measure such distance using a ruler. You will need to do calculations to find the distance AF. And so there will be some homework questions of this type for you to attempt. And so make sure you do your homework. Right, next, let's go to part C. Part C says, suppose that the locus of Z is a circle with center 2, 3, and radius 1, how can we measure the minimum and maximum values of argument z? Okay, so this one, it gives us some numbers, so we can really do calculations here to find the minimum and maximum values of argument z. So what is the meaning of argument z? Argument z can always be interpreted as argument of z minus 0 plus 0i. And the geometrical interpretation of this is angle from 0, 0 to z. So they already tell us that, okay, let's just draw out the Argand diagram. Okay? Let's just draw it out accurately, so you can see accurately what's happening. Okay, 2, 3. It's here, and radius 1. So I will need a point on the left, a point on the right. Okay, a point above, a point below. So this is the locus of z, and you have a radius of 1 unit. Yeah, so it's a circle with center 2, 3, and radius 1. And how can we measure the minimum and maximum values of argument z? And so argument z, as interpreted just now, is angle measured from origin to z. And so z can be anywhere along your circumference of the circle. So there are infinitely many possible values for argument z, since z can be anywhere. Right? But one thing for sure is that you must measure your angle starting from the origin. Okay? So I will draw a horizontal dotted line from the origin. Okay, so if my z is here, okay, then I would measure argument z like this. If my z is here, and then I would measure my argument z like this. So out of so many different possible values of argument z that I can get, what is the minimum? What is the minimum angle that I can possibly get? So in other words, you have to imagine that uh, you place your ruler. Imagine that you place your ruler like this, and you start to rotate your ruler. You start to rotate your ruler. Start to rotate your ruler. Then yeah, you rotate your ruler about the origin because you are trying to measure the angle starting from the origin. You rotate your ruler. The first time your ruler touches the circumference of the circle, that is where uh, that is a direction that will give us the minimum value of argument z. Okay. If you rotate your ruler using the method I described just now, okay, the first time your ruler touches the circumference of the circle, it will be roughly here. It will be roughly here. So in other words, this dotted black line, it would be a tangent line to the circle. And this black line would be a tangent line to the circle. Then this angle here, which I label as alpha, okay, it will be the minimum value of argument z. Alpha will give you the minimum value of argument z. Then what about the maximum value? For the maximum value of argument z, you will have to keep rotating your ruler. You keep rotating it. Then you will try to figure out when is the last time your ruler touches the circumference of the circle before it stops touching the circle. Okay, so that will be a tangent line to the circle on the other side. Let me just draw my circle nicer so that uh, there will be a tangent on the other side, which is roughly here. Okay, so if I call this angle as theta, then theta would be the maximum value of argument z. Because the point of tangency is the point where the tangent line touches a circle. Let's call it point B here. This point B is also a possible position of z. So in fact, the direction of OB, that is a direction that will give me the maximum possible angle that I will get when I measure the angle from origin to Z. The direction of OB, that will give me the largest possible angle when I measure angle from origin to Z. It wouldn't be possible for me to get any larger angle. Because if I want an angle to be even larger, then my line, for example, this red line here, it won't touch the circle anymore. So it will no longer be an angle from origin to Z. If I want to have a larger angle, then it will no longer be an angle from origin to Z. Yep. Right, so this is the method to find minimum and maximum value of argument Z. And so just interpret it as angle measured from origin to Z. So the first time your line, I mean, when you rotate your ruler about the origin, the first time your ruler touches the circumference, that will be the smallest angle. And if you keep rotating, the last time your ruler touches the circle, that will give you the maximum angle. Yeah. And here, A and B, they are just two possible positions of Z that will give you respectively the smallest and the largest possible angle. Right. So how can we calculate those angles then? You will need to complete your right angle triangle. So because your black dotted lines are tangents to the circle, then for sure you will have 90 degrees here, 90 degrees here. Because radius must be perpendicular to tangent. For ease of referencing, I will just label center as C. So CA is a radius, CB is also a radius. I have a distance of R here, distance of R here. Now, recall from your secondary school knowledge that when you have two tangents to a circle, when you have two tangents to a circle from a common external point, let's call it P here, then it is a guarantee that the two right angle triangle form PCA and PCB, they must be congruent. Congruent means they must have the same size, which means CB and CA must be the same length. PB and PA must be the same length. And of course, PC is a common hypotenuse. And yeah, so not only the three corresponding sides have same lengths, you also have same angles. You also have equal corresponding angles, which means you have alpha here, alpha here. If this is beta, then this must also be beta. Because PCB and PCA are congruent triangles. Congruent means the triangles have the same size. Okay, so that the corresponding side lengths are equal. and the corresponding angles are also equal. Okay. Right, so let's go back to this diagram here. Okay. Yeah, so now in my Argand diagram, my OBC and OAC are congruent triangles. Okay, so I can expect this angle and this angle to be the same beta. So I'll just label both of these as beta. And so now I know that the minimum value of argument z, it must be alpha. Okay, while the maximum value of argument z, it is alpha plus 2 beta. So with that in mind, let's calculate the numerical values of alpha and beta. Okay. Let's calculate alpha first. Okay. So to get alpha is pretty easy. Okay. You just no, to get alpha, it's not that easy. We should get beta first. Right. So to get beta, um, you know the radius is 1. Okay. The radius is 1. Okay. And C is having known coordinates of 2, 3. Okay. So you can easily get the distance OC as square root of 2 squared plus 3 squared. And then this gives you set 13. Then looking at triangle OCA. OCA, where your CA is 1 unit and OC is set 13, and here you have your beta. So beta, it must be inverse sine of opposite over hypotenuse. But the reason is because sine of beta, you see sine of beta, it is opposite over hypotenuse, which is 1 over set 13. Okay, so beta must be inverse sine of 1 over set 13. Okay, from the diagram, it's very clear that beta must be acute. Okay, so inverse sine, your calculator in radian mode, 1 over set 13, you have 0.28103. You take 5 SF to avoid rounding error. Then, still using back the same diagram, the same Argand diagram, right, now we want to get alpha. Okay, now we want to get alpha. Okay, but we'll have to look at a different triangle this time. Okay, I call this point at x equal to 2, I call this point as f. Okay, then now I want to look at the right angle triangle OCF, okay, where your C is 2, 3, your F is 2, 0. And then CF has 3 units. OC, just now we know, it has set 13. And OF has 2 units. Okay. Then what is the angle here? Angle COF. Angle COF, it would be alpha plus beta. It's alpha plus beta. Okay, so now we can get whether you want to use sine, cos, or tangent is up to you. I just use tangent here. Okay, the tangent of alpha plus beta is opposite over adjacent, 3 over 2. So alpha plus beta is inverse tangent of 3 over 2. So alpha plus beta is 0.98279. Okay, but now we know beta is 0.28103. Okay, so you can put in 0.28103 that we got earlier. Okay, and from there you have alpha. You have this 0.70176. So when there's no unit for this angle, it's understood to be in radians. So now it's time to write down the minimum value of argument z. At the top right corner of your screen, just now we have already figured out minimum will be alpha. So it's just 0.702 to 3SF. Maximum value of argument z, that would be alpha plus 2 beta, which is 0.70176 plus 2 times 0.28103. We have 1.26 to 3SF. Yeah, so this is the way to find minimum and maximum values of argument. Okay, now we'll move to example 10, the second last example for this chapter. This is on page 31. Yeah? So you are given this equation. And find the greatest and least values of modulus z. First task. Second task, find largest and smallest argument z. Okay, so this one we know is an equation of a circle. Okay, this is actually a circle with center 2 minus 3 and radius 1. Okay, so we're going to draw it out in an Argand diagram. You have the center at quadrant 4. So I will leave more space to quadrant 4. They draw to scale. 2 minus 3. Radius 1, so I need 1 unit to the right of it, 1 unit above, 1 unit on the left, and 1 unit below. So let me draw the circle. Yeah, my circle here looks a bit ovalish because I didn't use a ruler to measure the scale. But if you measure your scale using ruler, it should be a nice looking circle. Right. Anyway, it won't affect my calculations. Okay, find the greatest and least values of modulus z. Okay, so modulus z should be interpreted as modulus z minus 0. So it is the distance from origin to Z. So this is distance from 0, 0 to Z. Oh, and by the way, to make my diagram more complete, I just label 1 here. Yeah, then that should be good enough. And this red circle is my locus of Z. Right. So distance from 0, 0 to Z, um, it is a distance from an external point to the circle. On the previous page, part A, on the previous page, part A, we have learned how to find distance from external point to circle. And the method was we have to connect a line from the external point, the 0, 0. We connect it to the center, and then we extend this line to the other side. We extend this line to the other side. So, and earlier we have learned that if the external point is P, and the center is C, then the shortest distance it will be PC minus R. Longest distance is PC plus R. Where I have an R here and another R here. PC minus R gives the shortest distance. PC plus R gives the longest distance. Right. So the shortest distance from 0, 0 to Z, that will give me the minimum value of modulus Z. Okay. So this point, for easier referencing, I will just call it C here with coordinates 2, minus 3. Okay. So I will first find the distance from O to C. So OC will be square root of 2 squared plus minus 3 squared. That gives me set of 13. Right, then the least value of modulus Z, it is OC minus the radius. And so I'm just using the PC minus R formula here. Here our external point is O. So it's OC minus radius, which is set 13 minus radius is 1. And that's it. We are not going to convert this into decimal form because this is a pure maths paper. We'll just leave it in set form. The greatest value of modulus Z, that will be OC plus radius. Right, so that will give me 13 plus 1, and that's it. Okay, so we are done with the first task. Greatest and least values of modulus Z are done. Okay, then next, smallest and largest argument Z. Let me just erase this 2 minus 3 here because I will need this diagram. I will draw 2 tangent lines later. This diagram becomes part of your working. So later when I label the angle alpha and beta on my diagram, the examiner will be able to see what my alpha and beta mean. So So largest and smallest argument z, what is the meaning of argument z? Argument z is argument of z minus 0. Okay, so it is angle from 0, 0 to z. Angle measured from origin to a point on the circumference of the circle. And so what is the smallest possible angle and the largest possible angle? And so here, when they talk about largest and smallest, um, they are looking at the value of the angle as on the number line. I mean, um, if I mean minus 0.7 will be treated as smaller than minus 0.4. This will be smaller. Right, so here, because we have negative angles, the smallest argument r will be obtained by this tangent line. Right, so this tangent line will give us a direction of the smallest argument z. While this direction about this direction, it will give us the largest argument z. First of all, we know that the two required angles here, they must be obtained by drawing two tangent lines to the circle. So we know one of them must be smallest, the other must be largest. But which one is smallest, which one is largest? It depends on which one is more negative. And since both angles are going to be negative, the more negative one will give us the smallest. So the smallest that the meaning of smallest here is that if one angle is minus 0.7 and the other is minus 0.4, then minus 0.7 will be treated as the small one. Yeah, of course, these angles are not minus 0.7 and minus 0.4 because I haven't done any calculation, but just to tell you the idea. Okay, so in the diagram, I'm going to label some alpha and beta there. Yeah, so this alpha is just a magnitude of the angle. This beta and this beta, I know they will be the same. And yeah, I will also have this points of tangency, and let's call them points A and B. So OCA and OCB are congruent triangles, and that's why I have the two equal beta set. Okay, so just like the previous page, it will find beta first. Beta is usually easier to find. CA and CB, they are both radius. They are both radius. So I just make use of either one of these two triangles. Here I just use OAC. You can draw a separate diagram here if you think this diagram helps. Well, AC is the radius, which we know is 1 unit. OC, we already had it as 13 from our previous calculation. OC, we had it already. And our beta is here. Right, so making use of this right angle triangle, beta will be inverse sine of opposite over hypotenuse as 1 over 13. And that would give us 0.28103. And then next we can find alpha. So to find alpha, I will call this point at x equals to 2. I will call this point f. Okay, so we'll use the right angle triangle OFC like this, where my OF is 2 units, FC is 3 units, and here's my angle alpha plus beta. FOC is alpha plus beta. So I know alpha plus beta is inverse tangent of opposite adjacent, that's 3/2. And that gives me 0.98279. So my alpha, that's 0.98279 minus beta, point 28103, and now I have 0.70176. Okay, now it's time to state what is the largest and smallest argument Z. Okay. So our smallest argument Z, for argument Z, we have to take into account the direction. So we have negative angle here because this is an angle in quadrant 4, right? So the magnitude of the angle will be alpha plus 2 beta, but we have to take negative of the entire thing because the angle is measured this way in the clockwise direction. So it is negative of alpha plus 2 beta. Okay, negative of the entire alpha plus 2 beta. That's negative of alpha, just sub in 2 beta and you have negative 1.26 to 3SF. And then your largest argument Z, well, I better write it down there. To write down the largest argument Z. Okay, according to my diagram, the magnitude of the angle will be just alpha, but I have to take the negative of it, so it's negative alpha, which is negative of 0.702 to 3SF. Okay, so here are your two final answers. Smallest argument Z and largest argument Z. Okay. There are just some additional comments here. So if you compare these two values on a number line, if 0 is here, negative 0.702 is here, negative 1.26 is further to the left. Okay, so the number that is further on the left on the number line is regarded as smaller. This is regarded as comparatively larger if we compare between negative 1.26 and negative 0.702. Okay, the one on the left is regarded as smaller. Okay. Yeah, so it makes sense to have negative 1.26 as the smallest and the negative 0.702 as the largest. So just don't get confused between smallest and largest when you have negative angles. We'll just follow their relative positions on number line to decide which one is small, which one is big. Okay. Last example of this chapter, example 11. But this will be a challenging one. To illustrate on a single Argand diagram the locus of the point representing the complex number z that satisfies both of these inequality. So they want us to draw out, draw on the Argand diagram, uh, the locus of the point that satisfies both of these inequality. For inequality, you expect to have some shaded region. Then part one, they say find the greatest and least values of modulus z minus 2. But before that, we have to first draw the Argand diagram. So let's interpret this thing, minus 3 pi over 4 less than argument z minus 3 minus 3i less than equals pi over 2. In this argument, I'll just factor out a negative here so that I have 3 plus 3i. And then this is actually the angle from 3, 3 to z. Yeah, these words in green you don't really have to write out. I'm just writing it out to tell you how to interpret this. Then what about the other inequality there? You again factor out a negative. Okay, so this is a circle. So again, this description you don't really have to write out because they don't ask for a description. Circle with center 3, 3 and radius 2. Shade the interior and include the circumference. Okay. And now we know what to draw. So we'll have to take okay, so the first inequality in blue on the left, it will give you some region. The second inequality, it will also give you some shaded region, and we have to take the intersection of the two because they want both inequalities to be satisfied. It's an AND connector here. So we have to take the intersection. Okay, I will draw the circle first because it's actually easier to start from the circle one. Okay. Okay, now let's draw the diagram. When you are drawing on paper, please use your ruler to measure so that your diagram is accurate. Use dotted line to align the position of your center. Okay. So you have your center 3, 3, radius 2, 2 units to the left, 2 units to the right, 2 units below, 2 units above. So now I have these 4 points to guide me when I draw my circle. Because this circumference will be included, so I can use a solid line to draw my circumference. Okay. Right. We are we should shade the interior, but we'll not shade yet because we still need to satisfy the other inequality. So uh, to satisfy the other inequality, it will need a half line starting from 0.33, which means the center of the circle, which happen to be also 0.33, it should be drawn using an empty dot. So I should uh, draw empty dot here. I should draw empty dot here. And I need a half line in the direction of minus 3 pi over 4. And minus 3 pi over 4 is minus 135 degree, so it makes a 45 degree to the horizontal. And it should pass through the origin nicely. It's a strict inequality here, so I have to draw using dotted line. So this is my 3 pi over 4 angle in the clockwise direction, measured from the positive x direction, from the 0.33. That it will pass through the origin. And because it's a 45-degree line, so if it covers 3 units vertical, it must also be 3 units horizontal. Okay. Then for pi over 2, because there is equal sign, I have to draw using solid line. To draw using solid line. So this will be 90 degrees. Okay. Okay, so okay. The region to shade will be the region to shade will be the region at the interior of the circle because we'll have to satisfy the second inequality. And at the same time, to satisfy the first inequality, we have to make sure that when we take any point in the shaded region, the angle measured from 3 to the point in the shaded region is somewhere between minus 3 pi over 4 to pi over 2, which means we should only shade this portion of the circle that is between the slanted dotted line and the green vertical line, and also in the interior of the circle. Yeah, so this will be the correct shaded region. Yeah, this will be your locus of Z. Uh, right. The radius of the circle is actually quite clear from our diagram, and because we plotted some points which are 2 units above, on the left, on the right, and below the center. But anyway, if you want to make it even clearer to your examiner, you can just choose to label like this radius here and write 2 units there. Yeah, so our diagram is done for now. And let's move on to part 1. Find the greatest and least values of modulus z minus 2. Okay, so let's talk about the idea first. What is modulus z minus 2? It is modulus of z minus 2 plus 0i. And its geometrical meaning is distance from point 20 to z. That's the meaning. So we'll need the point 20. 20 is here. That I'm blackening. The point 20 is that. This is 20. Okay. So Z is anywhere in the shaded region. Anywhere in the shaded region. Okay, so well, this shaded region is having the form of a circle. So where would be the shortest distance from 0 to any point in the shaded region? It will be somewhere here that I'm coloring in yellow. And to get exactly where that point is, it will use the usual technique of finding uh, the distance from external point to circle. Okay, so to get exactly where this point is, then you just need to connect a line from the center of the circle to the point 20, and then you extend it to the other side. So yeah, so this yellow colored point, the intersection between the circumference and my black dotted line, eh, at that point, it will give me the shortest distance from 20 to Z. And the other point that I'm coloring in light blue at the other side of the circle, that will give me the longest distance from 20 to Z. Okay. Yeah, we can take this yellow and that blue point because they are part of the shaded region. Yellow and blue point, they are both part of the shaded region. That's why we can take them. Right. So it's time to do the proper working. The idea part, you don't have to write out actually. This one no need to write out. Now here comes the proper working. Okay, so we know for the distance from external point to circle, the shortest distance is PC minus R, longest distance is PC plus R. So for easier referencing, I will just call this point as C. I'll just call this point as C. Yeah, I label the word point C on my diagram so that the examiner will know what my point C refers to. Right, so the point 20, I'll just call it A here. So, or simply P, right? Since we are more familiar with PC, let's call it P. Right, so let's find the distance PC. Okay, by using distance formula, C has coordinates 3, 3. So I have 3 minus 2 squared, 3 minus 0 squared. That gives me sort of 10. Then it's time to write the least value of modulus z minus 2. Okay, that would be PC minus the radius. PC is third of 10. Radius is 2 units and that. Okay, next, greatest value of modulus z minus 2. That's PC plus radius. Okay, so this will actually give me the distance from point P to the light blue colored point there. That's certain plus 2 and done. And so this is the proper working for part A. I mean for part 1. Okay, so part 1 is done. The next, moving on to part 2. To determine the values of A and B such that argument Z is bounded between A and B. So this is just another way of asking what is the range of values for argument Z? So this is just a way of asking find range of values of argument Z. And they want us to find the lower bound and the upper bound. So to do this, we have to look back to our diagram. So looking back at our diagram, argument of Z, it should be interpreted as the angle measured from origin to Z. Argument Z is angle measured from origin to Z, and Z can be anywhere in the purple colored shaded region. So since origin is where we should start measuring the angle from, you imagine that you rotate a ruler about the origin. So the first time you touch the shaded region in purple, it will be when your ruler is, yeah, just draw in blue here. It will be when your ruler is tangent to the circle. So it's roughly here. When your ruler is tangent to the circle, that is when the first time, I mean, that will give you the smallest possible angle measured from origin to Z. Then, if you keep rotating, the last time your ruler touches the shaded purple colored region, it is not the other tangent, it's not this one, it is not this, it's not this. Because at this side of the circle, there's no shaded region. So locus of Z is not on the other side of this circle. So it's not this blue line that I just draw here. So we should not take this. And then what should we take instead? And so you carefully rotate your ruler about the origin and look at when is the last time your ruler touches the shaded region in purple. It should be this point at the very top. It should be that point. Yeah, so this direction will actually give you the minimum argument Z. This direction should give you maximum argument Z. You don't really need to write out the words minimum argument Z and maximum argument Z. You don't really have to write out the words, you just have to know. Okay. Now I just erase these words since they are not necessary. Right. So let's find the minimum argument Z. So I will label some angle here. Okay. I will call this angle as alpha. And I will need also a right angle triangle that is formed using the tangent to the circle. And let's call this point T, right angle here. And let's call this angle beta. Yeah, I know it's a bit hard to see now in the diagram. So I will just draw a separate diagram so that it's easier to process the triangles that we have. Okay, so I have my point C here. I'm looking at CTO. It is right angle triangle. Okay, OC, the distance. Uh, do we have OC just now or we didn't? Okay, so we have to calculate OC ourselves. Okay, so OC will be square root of 3 squared plus 3 squared. That gives surd of 18. CT is radius, which is just 2 units. Next, we can find this angle, which is beta, according to our diagram. COT is beta. So beta will be inverse sine of opposite over hypotenuse. That's 2 over surd 18. Calculator in radian mode, that should give you 0.49088. You write 5 SF because it's not the final answer yet. Okay. Then how do we get that alpha? Because alpha is what we need eventually. And so we'll make use of this right angle triangle formed by using the point 30. And so this point, let's just call it point F with coordinate 30. Okay, and now I will focus on the right angle triangle OFC, where C to F is exactly 3 units, O to F is also 3 units, and this angle COF, it will be alpha plus beta. Right. So now I have alpha plus beta. It is inverse tangent of opposite over adjacent, which we know this would give us inverse tangent of 1, which is pi over 4. So our alpha will be pi over 4 minus beta, which is pi over 4 minus 0.49088. And that would be 0.295 to 3SF. And therefore, uh, the question asks for A and B. Uh, since this will be the lower bound of the argument Z, it's a lower bound of the value that argument Z can take. So A is the same as alpha, which is 0.295 into 3SF. Okay, so that's A found. Or maybe it's better for me to just state A and B at the end. Yeah, I just calculate the other angle first. Okay. I also want to find the maximum argument Z. So let me just call the point at the top as G. Okay, so this G has coordinates 3, 5. Okay, so I'll use the right angle triangle GOF. 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 OF is 3 units, GF is 5 units. Let's call this theta. So theta will be inverse tangent of 5/3. And that gives me a 1.03 to 3SF. Okay, so now we know that the least value of argument Z, it is actually the alpha according to our diagram. And that would be 0.295 to 3SF. Greatest value of argument Z is actually the theta that we have just calculated. And that would be 1.03 to 3SF. So A is 0.295, B is 1.03. Because A should be the least value and B should be the greatest value. And there we have it. Right. So that's all for this example. And that's also the end of this chapter. So make sure that you do the homework. The homework solutions for this chapter has already been uploaded onto Google Drive. Right. That's all for the lecture videos for P3 Chapter 10 Complex Numbers. And I'll end this video.